Hey, chemistry. Trying something new. We're trying something new. Gonna try out OneNote for a bit here, just because it is much more responsive. The other app that I had been using there for a bit was getting a little laggy because they were just like I was adding a bunch of pages. I kept adding in graphics, adding in writing, and I really didn't want to make like a brand new thing because I didn't want to lose track of where I was. Anyway, if I hate this, I'll go back to whiteboard. I'll make a new page. But I'm going to try this because it might be a little more organized and I might be able to do it from more than one place. We'll see. It's a work in progress. What we're talking about here is I'm picking up down on... Nope. This one? One of the... I swore... whatever. Picking up here on page 63, talking about electrons, because we just finished our little thermochemistry section. Page 63 talks about electrons, and it starts off with a little bit of review. Maybe you remember, maybe you don't. But if you don't, that's why we're going over it again. Hopefully the repetition will help you get there. Electrons are located in orbitals that surround the nucleus, and the specific definition for an orbital is the most probable or the most likely location that you'll find an electron. That's according to our wave mechanical model, which we talked about earlier in the year. Now, a bit of new stuff coming up, right? That electrons can only orbit in certain specified energy levels, each of which represents a distinct amount of energy. So they can be in the first, or the second, or the third. You can't be in between levels, kind of like a staircase or a building. You have to be on a level. You can't be in between. The levels themselves are known as principal energy levels, or PELs for short. All right, the higher the energy level is, the further away it is from the nucleus, and the more energy it has. Right? So this is, again, kind of review. We talked about that before. As you get further and further away from the nucleus, electrons have more and more energy. Another new thing, when electrons occupy the lowest level orbitals, or the lowest energy levels, then that atom is said to be in what we call the ground state. Right, so the ground state, the lowest level, the ground floor, when they're all in the lowest possible energy levels, it's in the ground state, so electrons are filling in from the bottom floor, and they're only moving up an energy level if that lowest level is full. So it'll fill up the very first level, and then if the first level fills up, then they'll fill up the second level. If the first and second levels are filled up, then they'll fill up the third level, and so on and so on. Right? Now, the ground state electron configurations are on your reference table, so they're already there. You don't need to do anything special. Sodium, this 281 is in the bottom left corner of the reference, or of the little box for each element. So there's two electrons in principal level 1. There are 8 electrons in principal level 2. There's only 1 electron in principal level 3. Right? If you subject electrons to heat, light, or electricity, so you give them a bunch of extra energy, they can actually absorb it, and they can temporarily jump up to a higher energy level. Getting used to writing in this new thing. So they can temporarily jump up to a higher energy level. This is an unstable condition. It's called the excited state. So you can get electrons to be excited. They jump up, eventually they will come back down. Right? So an excited electron will quickly return back down to a lower energy level, and it will emit, or it will give off, that extra energy that it did absorb in the form of light. Now, when we see light, we typically see it as like one color, right? Like this thing behind me is blue, this is black, my shirt is brown, my headphones are white. In reality, all of the light, all of the colors that we see are composed of lights of many different wavelengths. right? And each of them is viewed as a different line when you look at it through right. And I'll write that word out here too. Oop. I think the way I'll do it, I'll use the white pen. Just to repeat, it's a spectrophotometer. Spectro for color, photo for light, meter for measure. This is something to measure the different colors of light. Right? Spectrophotometer. Now, the lines are emission lines. You might see them called spectral lines, right? And the lines are distinct to each element. They're like fingerprints, right? So lithium is these 4 lines, cadmium is these 7, strontium is these 9 or 10, right? 9. If you look, right, you see that this is a mixture down here. So it's a mixture of multiple, some number of these 3. Well, lithium has lines that line up perfectly with the mixture. Cadmium, if you look, these 2 lines are not in the mixture. That means the fingerprint is missing. Cadmium is not in this mixture because these 2 lines are missing. But strontium is in the mixture because if you look, you can line them up. They all match up. Excuse me. If you are given a diagram like that one down there, then what you need to do is read the question first. But the question will probably ask which of the following elements is not in the mixture, or the mixture is composed of which of the following elements. So just make sure to read and appropriately identify. All right. Moving forward, the Bohr model and Bohr diagrams are review. Right. We have the planetary model, which we found out later was not quite right. It was mostly right, but it's not exact circles, it's just kind of regions, right? The orbital is a region of space. Magnesium, if I check my reference table, has a configuration of 2-8-2, which means 2 in the first level, 8 in the second, 2 in the third. Now, this center represents the nucleus, which will, I was going to write how many protons, how many neutrons, but if you look on the bottom, it's mostly just filled in. Bohr diagrams don't worry about the nucleus, they worry about how many electrons are there on each level. Well, there's 2 in the first. There are 8 in the second, and then there are 2 in the third. I space them out as best I can just because they're all negative, they don't want to be near each other. Very quickly, if I look at these, and I think I need to do this. If I go and hey, look, a reference table. Another nice thing about this, so I can keep all I can keep all 3 sections in here. Now I realize this is a little sideways, but sodium, if we look down here, I don't know if this, oh, it does do what I wanted to do. Awesome. All right, so sodium has a configuration of 2-8-1. Potassium is 2-8-8-1, and hydrogen has a configuration of just 1, right? And those are the 3 elements that we're looking at here. Now what I'm going to do down here is I'm just going to write the configurations out just so that I know them. And this is 1. But again, 2 dots here, 2, 3, 4, 5, 6, 7, 8, 1 out here. You can do the same thing with these. Bohr diagrams are not super difficult. They're kind of nice. If you're asked to just draw a Bohr diagram, take the win. Right, you won't do any Bohr diagrams above like calcium. Calcium is the biggest one that you would see. It's 2-8-8-2, so that's 20 dots. That's kind of the upper limit on the Bohr diagrams that I've ever seen. The last thing I'm going to talk about today are valence electrons. Right, an atom's outermost electrons have a special name, we refer to them as valence electrons. The reason that the outermost shell gets a special name is when two atoms are interacting with each other. Let's say an atom of lithium, right? So this is lithium, which is 2-1, interacts with fluorine, which is 2-7. So here's a fluorine nucleus. There's 2 here, and then it has an outer shell. 1, 2, 3, 4, 5, 6, 7. All right. If these two were to like come at each other and collide with each other, again, this is lithium, this is fluorine. If they were to come at each other and collide with each other, the first thing that would interact is this outer shell. All right, this section out here. This outer shell of fluorine and this outer shell of lithium, they're what's going to interact. And because that outer shell is the first thing to interact, these outer shells, that valence shell, or the valence electrons, are going to determine how they behave, right? This is how they shake hands. This is how they first interact with each other. This is a first impression. If you want to look at the valence electrons for a specific element, you just look at its electron configuration, and you find the last number. That last number tells you exactly how many valence electrons it has. I really hope fluorine is 2-7. It's going to be very awkward if I got that wrong. I think it's 2-7. I'm going to stick with it. I'm going to double down. I'm going to stand by it. I'm also going to check, because now I suddenly don't trust it. Fluorine. No, we're good. 2-7. Okay. But again, that outer shell, those valence electrons, are the first things that will interact. So the number of valence electrons is responsible for the chemical behavior of the atom. Right? Now the other thing to note is that when we talked about ions before, ions will gain or lose electrons. They'll do it from this outer shell. So this outermost shell, that's where electrons are going to be gained and lost. Alright. Now, if you look, there's more stuff on page 65. I'm not going to worry about it. Ooh, that's interesting. I clicked on the wrong pen. That's kind of cool, though. I'm not going to worry about this on page 65. I'm not going to worry about this on page 66. And I'm not going to worry about the very top part. Ooh, hello? There we go. Very top part of page 67. I will come back to some of these questions because I like them. I'll probably review them next class. What we're going to start next class is something about this topic up here, the topic of excited electrons and the excited state. So we're going to do a quick lab about that. And then we'll also go over some of these questions. We'll go over the lab questions. And later this week, we'll start to talk about oxidation and reduction. This is a kind of tricky thing, but I'll get you through it. We're gonna power through it. Big deal is there are gonna be a bunch of phrases for you to remember to help you do this section. They're gonna be kind of wacky. Bear with me. I promise they will help. All right. In the meantime, nothing extra, nothing crazy tonight. Just be ready to do the lab. Fully remote students, look for the video that will go with the lab. It'll go up in the lab section. Until next class, until next video, I will see y'all. Take care of yourselves, kids.